Hello everybody and welcome back to the extension video for Gravitational Fields 7. Now, as I alluded to in Gravitational Fields 7, we've got this thought experiment of, well, what would happen if we were to drill a hole all the way through the centre of the Earth? And what we'll do is we'll take it one step further and we'll say, well, if you dropped an object into that hole, what would happen to it? Probably pause the video at this point and have a think, maybe sketch your ideas down and then come back once you think you've got a rough idea about how you think this is going to play out. Now, the answer to this, bizarrely, is frustratingly simple. Now, again, we're going to go back to this assumption that density is a constant. And again, going back to the main video, we had the equation G is equal to minus 4/3 pi G rho multiplied by R. Now, with this equation, if we just have a look at the units for a moment, we obviously know that the unit of R is going to be metres, and the unit of G is newtons per kilogram. But obviously, we've shown in previous videos that that has an SI base equivalent of metres per second squared. In other words, it can be treated as an acceleration. We've also got in the middle the 4/3 pi G and rho. We have a load of constants. Now suddenly we're starting to see something which looks familiar to us. If I just put underneath, going back to simple harmonic motion, sorry, not R, of course that's going to be X. If we go back to the general equation for simple harmonic motion, then suddenly we can see some similarities. Unit of X will be metres. Unit of acceleration will be metres per second squared. Omega is a constant, and obviously we can also see that we've got minus signs as well. So suddenly it's all just falling into place, and it's all been right under our nose without us actually realising it. That body would undergo simple harmonic motion. So now that we know that, again, in theory, of course, if we were to do that, it would undertake SHM, what you can do is have a go at calculating the time period and the maximum velocity. So once again, pause the video, go and do your calculations, and then come back when you think you're done. So let's do some working out first, of course. We're obviously going to aim for the time period first and foremost. Let's remind ourselves of the equation. G is minus 4/3 pi G rho times R. And what that means, as I said, when we compare that to minus omega squared x, what that means is that it's this bit here, not including the R. Just be careful to show that. Okay, not including the R, it's the 4/3 pi G rho bit that we are going to match and therefore equate with omega squared. Now, the next stage, I'm going to substitute back in for the density. So, remembering, of course, that density is mass over volume. So that will be mass over, bearing in mind that we're dealing with a sphere, 4/3 pi r cubed for the volume of a sphere. So when we plug that one back into the omega squared equation, then we have omega squared is equal to 4/3 pi g, that's the original bit, and then the substitution is m over 4/3 pi r cubed. Now the reason for doing that is you can see that the 4/3 pi on the top and bottom cancel each other out, and what we're left with is that omega squared is g times m over r cubed. To carry working that through then, we're obviously looking at the time period first, as we said, so remember that omega is 2 pi over t, and therefore omega squared is 4 pi squared over t squared. So let's substitute that one in as well. So 4 pi squared over t squared is equal to gm over r cubed. Take the inverse of that, and I'll come all the way up here, so t squared over 4 pi squared is equal to r cubed over g times the mass, and that's starting to look devilishly familiar. It's starting to look exactly like Kepler's third law, of course. So following it through, t squared is going to be 4 pi squared r cubed over gm, and then when we square root that, t is equal to 2 pi multiplied by the root of r cubed over gm. And again, bearing in mind that we're dealing with SHM, we can see that there are similarities with the SHM equations there. Both the mass on a spring and the simple pendulum both start with t equals 2 pi root of something, so hopefully you can start to see how a lot of these things, at least from a theoretical view, are going to start to tie together. Now, of course, using all the standard values that we've been using all along, and obviously they're on the data sheet, because we're talking about the Earth, we know that R is 6.37 times 10 to the 6 metres, 6,370 kilometres, and that the mass of the Earth, of course, being 5.98 times 10 to the 24 kilograms. Now, when you work all of that through, you end up with an answer of 5,058 seconds, and that's the 4 sig figs, and that would be the time period of oscillation. Now, think about that. It would be the time that it would take if we dropped a ball in at school. It would go all the way through to the other side and come back in 5,058 seconds. Now, if we divide that by 60, we can see that that is approximately, it's just over 84 minutes. Now, of course, if we think about this, if we were to drill a hole all the way through the centre of the Earth and out the other side, of course, from a longitude and latitude point of view, we would end up popping out somewhere south of the South Island of New Zealand. It would be in that ocean somewhere. But of course, if we were just to do a one-way trip, it would be half of that, and that one-way trip would only take us, therefore, 42 minutes. So it's a far shorter journey time, in theory, than the 24 hours it would take us on the plane to get to New Zealand. Now, as far as the maximum velocity goes, again, we'll come back to our SHM equations, and we know that the maximum velocity is omega multiplied by the amplitude of oscillations. Now, the amplitude of oscillation in this situation is just the radius of the Earth. And of course, from the last slide, we've at least got omega squared as being equal to gm over r cubed. So when we substitute all of this in, Vmax becomes, obviously we're square rooted, so root of gm over r cubed multiplied by r. Now, just to tidy things up, we can bring the r inside the square root. We're left with gmr squared over r cubed. We can do some cancellations with the r's, and we're left with root of gm over r. Now once again, all standard values there, so when you plug all of that in, we get that the maximum velocity is 7,913 meters per second, or in other words, we're getting very close at that point to 80 kilometers per second, and obviously that point would be at the center, exactly at the center of the Earth. So thanks for coming into this extension video. I hope you enjoyed that. I hope you got something useful from it. Hopefully that was a little bit of fun, at least from a physics point of view, a little bit outside the ordinary and a little bit outside the syllabus, but interesting to see nonetheless.